bodies of land ice coming into the ocean. And as we also heard, that causes you polynyas to form, and you get frazzle ice in these polynyas. But what I'm really interested in is the frazzle ice that forms underneath the land ice. So let me just give a little sketch. This is my favourite sketch of this very well-known process. On the left-hand side, we've got an ice shelf, and ice shelves can be hundreds of meters thick, thousands of meters thick. But on the right-hand side, much more importantly, we've got some sea ice. So the emphasis is on the sea ice. Sea ice is growing because of heat flux to the atmosphere. As it grows, it rejects brine, cold, dense brine, into the ocean. And by a bit of magic, the oceanographers know about that, ends up under the ice shelf and causes melting there. Because that water is melting fresh ice, then a plume develops. So this is less dense, that plume rises, and because of the pressure dependence of the freezing point of seawater, you get nucleation of ice crystals. So this water can become in situ supercold. Frazzle ice appears there by some process, and under ice shelves it's called marine ice. For some bizarre reason, not my fault, under sea ice it's called platelet ice. And it's this platelet ice that I want to explore. It's largely an Antarctic phenomenon because around Antarctica sea ice is quite likely to abut, coastal sea ice is quite likely to abut an ice shelf, whereas in the Arctic that's a much rarer concern. And many of the observations I'll show are from this little area of Antarctica here in McMurdo Sound. So here's the phenomenon we're looking at. I like this picture. Let's see this little video clip. I believe if I just do that, it'll work. This is entitled Underwater Snowstorms Do Happen. Please ignore the distracting biology. What you're focusing on are these tiny little specks. And these are ice crystals that appear in the water. They kind of appear like a snowstorm. It's a sort of weather event. They happen episodically, and they come up, and they accumulate under the sea ice. Here we see the bottom of the sea ice with the little puffy accumulations of that, the ice crystals there. And close to the ice-water interface, the supercooling is largest, so these crystals can grow very large. Here's Natalie looking very happy because she's found a big one. They also accumulate on anything you put in the ocean, so on the lines that are holding oceanographic instruments. And here's a rope being lifted out with some of these crystals attached to it. And underneath you get an accumulation of crystals, which we call the sub-ice platelet layer, following lots of other people. This is a friable, porous layer, and it's this particular layer that I want to focus on. I want to focus on how this layer turns into this. So these are thin sections of sea ice. So this is sea ice once it has grown so that it has very low porosity. And we're taking thin sections, so samples, very thin slivers of ice, and looking at them in cross-polarized light. And what you can see, the different colors are different crystals of ice. So this is a sample that's about 8 centimeters long. And when we have no influence from the ice shelf, you see that you get long column crystals, so it's called columnar ice. When the ice shelf influences things, then we end up with platelet ice, which is a much more disordered sort of vertical structure. So over the years, this is the sort of picture we've built up of what's going on here. Let's have time, starting on the left-hand side and progressing to the right-hand side of the slide. The solid line here is our sea ice base. And by sea ice base, I mean the hard sea ice. The sea ice you could get if you take a core and pull it out, then it comes in the core barrel. At some time in the winter, though, we start to get this flux of crystals that we saw in the video, and they can accumulate in this porous layer underneath, and this will have some kind of an ice volume fraction. We tend to call it ice volume fraction rather than porosity. It's just 1 minus beta. Now, to go a bit further, we needed some models, and there are many very nice models of frazzled ice growth, as we heard from Danny yesterday, mostly based on the work of Steve Daly from 1984. And they all begin with nice little disc-shaped crystals. These are disc-shaped crystals measured in a river with an unpronounceable name. There's a lovely paper by McFarlane quite recently that looks at the distribution of crystal sizes in this river. And what you need to consider when you do that is to think about nucleation, secondary nucleation, and heat mass transfer between the crystal and the fluid. But we wanted our model for a slightly different purpose. What we want to do is go to the sea ice in the springtime and ask the sea ice what happened in the ocean during winter. So we needed a model that takes into account crystal orientation, because that's the thing we can measure. So in this model, our crystals have to be flat plates. So these are some observations of crystals. We want to know where the c-axis direction is. Doesn't matter what that means, it's just a particular crystal direction. We want them to get thicker. They grow with a high degree of kinetic variability, so they grow much faster on the basal plane than they do perpendicular to the basal plane, and they have dendritic edges. So, smart student I had did this modeling. What he did was take some polygonal shapes. He made them dendritic by putting a cosine function around the edge, and then he let this crystal expand in all directions, preserving shape. And the growth rate is just a constant. So then he put together an initial layer to make his base, to which he's going to add crystals to simulate. He allows these to get bigger according to some rules, grow in some grain boundaries, and then, having formed the initial layer, which is at the top of the picture here, we let crystals come up. So these crystals, well, it says it's a buoyant rise. In reality, in the model, they just get there. And then they find a mechanical equilibrium. So this is just a purely mechanical model that just allows crystals to come in. So here's the sort of space there is. So you have a grid following the rules in the Voronoi dynamics condition, which simply looks at the relationship between the position of the crystal and some growth rate, which and the only growth functions are on the basal plane and in the c-axis direction, so that's the only difference. What we end up with, is switching off the entire thing. Try that one. Here we go. So you get a set of crystals that grow into your volume, and it's a three-dimensional thing. We can take a horizontal plane through that. On the middle right, our virtual sea ice is a horizontal plane through that crystal. We can color them, and then we can just make our simulation look like our real sea ice. So these little dots on the plot are representing the crystal orientations, and all we're looking for is a statistical similarity. So that's just illustrating that that works. So what we got from this model is a few things. First of all, that platelet ice is always going to be disordered. Even if you start with a flat plate, it ends up disordered, and it didn't seem to matter which way these crystals rose up from the ocean. We also got a condition for when the subice platelet layer would form. And so basically what it is, it's when the number flux of crystals from the ocean, if that's larger than the rate at which the ice-water interface is coming down and stopping these crystals growing, then you get a subice platelet layer. But because it's mechanical, it doesn't tell us anything about the porosity of the layer. So Pat Wongpan then put some heat mass transfer into the growth function, so that we could now have our crystals coming up from the ocean, filling the spaces, and then allow them to grow by diffusive heat and mass transfer. And the lower section there is his model of the ice-water interface of this platelet ice and the reality up above. And I'll show you in a minute that this gives us some measure of some model of the porosity, which actually agrees very nicely with Dirk's group's model. So here's our picture now of how platelet ice forms. We've seen the bit on the top first, but underneath now we've plotted the heat fluxes. So the top brown line shows the conductive heat flux as a function of time, going upwards to the atmosphere to grow the sea ice. And underneath is the heat flux to the ocean. Now, when these platelet ice crystals start to appear, what we have is effectively a heat loss to the ocean. And that's what's quantified here. Whoops. Quantified on the right-hand side very simply. We simply see that the heat loss to the ocean accounts for the platelet ice that has been grown at the base of the sea ice. And our measurements would say, all right, so that's about 25 centimetres in a 2-metre ice cover when you're 10 kilometres away from the ice-water interface. 10 kilometres away from the ice shelf edge. So using this parameterization of oceanic heat flux, we can now use measurements that have gone on in McMurdo Sound for over a century, actually, to make a map of what we think the ocean heat flux is in McMurdo Sound. And the thing to notice here is that it's quantified, here's an incompatibility. All these little rectangles are meant to be minus signs on the scale. So the oceanic heat flux goes to minus 40 watts per square metre, which is actually quite a large heat flux. It's similar to heat loss from an open lead, for example. And you can see that there is a plume of cold water coming out from underneath the ice shelf. So we might want then to use an ice shelf water plume model, and again there's a huge amount of work being done on that by some members of the audience. I won't say anything about them except that they can be 1 or 2D, they can have Coriolis in them, and they can have crystal size classes. So they can have crystal growth in them, and the picture here is from Smedrud and Jenkins, which is a particular model that was adapted by a student I had who looked at how far an ice shelf plume would come out under the sea ice. And he did that because we have some observations that we compare with that sort of a model. But you can see we can't go very far north. We can only get to about this point to make observations. And it would be nice to have observations going further north. And to get observations going further north, we're therefore going to have to go to the sky or have some kind of remote sensing observation. Now, if we're going to be measuring something remotely, we need to have a property to measure. And incorporated platelet ice, this platelet ice once it's frozen in place, is not a good candidate. And it's not a good candidate because while it's very different from columnar sea ice when you look at the crystal structure, the salinity of incorporated platelet ice is just like the salinity of platelet ice. And we also believe that the permeability of and the porosity of incorporated platelet ice are very similar to columnar ice. So we're not going to be able to detect that remotely. The sub-ice platelet layer, on the other hand, is extremely porous. And I've put down some observation ranges here. Pat Wongpan's modelling said about, so we're going to be in ice volume fraction about 0.22. Observations, there's a whole range of these, and the sort of number I would choose is 0.25, but it's plus or minus 0.1. So it's a case where the error is as big as the measurement. And I don't know that that's entirely unjustified because I suspect that it's probably quite a variable quantity. It'd be interesting to see what Dirk thinks. We're going to use, therefore, electromagnetic induction techniques because they are able to detect changes in conductivity. And conductivity is going to be something that depends very much on the porosity or the ice volume fraction. And there's some very nice work done last year on, or published last year, on electrical conductivity made from multi-frequency electromagnetic induction techniques. And what they see, what their result was from Hunkeler et al., is that the ice volume fraction was in the range 0.29 to 0.43, or alternatively you can think of that in terms of a range of electrical conductivities. So the sub-ice platelet layer has a very variable and low ice volume fraction. That will affect the conductivity. Its presence is also going to affect the freeboard. And Dirk very kindly introduced the idea of cryosat and IceSat, which are satellite altimeter measurements of sea ice thickness. Underneath the sea ice, we're going to have this additional snow, if you like. So this is going to affect the freeboard. So let's make some measurements by airborne electromagnetic induction sounding. Now, these techniques have been used for many years to measure sea ice thickness. Actually, what you get is snow plus sea ice thickness. And the way it works in principle is this. You get a helicopter, and then you get an EM bird here, an electromagnetic induction sounding bird. This bird's called Rosie. And the principle is that there's a transmitting and receiving coil in the bird. It flies at a height of 16 to 20 meters above the sea ice. The transmitting coil, the transmitting coil produces electromagnetic waves which induce currents in the nearest conducting object. the nearest conducting material is seawater underneath here. So these induced currents then produce a secondary magnetic field which is picked up by the receiver coil. So you know the distance from the transmitting coil to your conductor, which is seawater, and with a nice laser altimeter you also know the height that you are above the snow. So you subtract one from the other and hey presto, you can get sea ice thickness. Rosie is a single frequency electromagnetic induction device. So she, rather than having multiple frequencies, only has a single frequency, but measures, we have two measurements, we have an in-phase and a quadrature measurement. It's usual when sea ice thickness is measured to have a two-layer model, but Christian Haas and Wolfgang Rack have run a three-layer model. So let me just say what the three layers are. So we have a transmitting and receiving coils separated by about 3 meters and at a height of about 16 meters above the sea ice. Sea ice is modelled as having a conductivity of 0. So sea ice is like air as far as the electromagnetic induction device is concerned. Underneath the sea ice we have a sub-ice platelet layer, and we're going to let that conductivity be anything between 0 and the seawater conductivity, which is our third layer underneath. And what's on the right hand side is the predicted forward model of the quadrature and in-phase measurements as for 2 meters thick sea ice, snow plus ice, as a function of sub-ice platelet layer thickness. And the main takeaway thing, or the message from this plot, is that there are lots of lines on it. These are for different conductivities of the sub-ice platelet layer, which we don't know. But the nice thing is, at least the quadrature and in phase measure something different from each other. We'd be really stuffed if they didn't. So here's what you get from the forward model. In phase on the left, quadrature on the right, and we have a number of different platelet ice conductivities. It turns out, I'll show shortly, that in fact they're going to be confined in the range from more than 600 to 1500, so essentially between the two coloured lines there. And the reason we think that is from this, oh dear, we seem to have lost the labels. So what we have here is mixture conductivity against porosity. And, oh dear, that's got lost too. So this is our estimate of porosity, or ice volume fraction. That was 0.25 plus or minus 0.9. And on here we have a range of possible conductivities from Hunkeler et al.'s work. So, oh, and the models, which you can't see, are the black ones are from Archie's law, which is the very basic porosity, permeability, conductivity, porosity relationship. And the red is from this model of DC conductivity for incorporated platelet ice. So basically all I want to say is that we're in this region here. So what I want to show then is essentially what happens if we fly away from the McMurdo ice shelf along a line in this direction, but for the moment I'm only going to be showing some transects, east-west transects, quite close to the ice shelf. So these transects will be at about 3 kilometres from the ice shelf, and that will be shown in magenta, and 11 kilometres from the ice shelf. So here's the electromagnetic induction in phase and quadrature measurements, plotted as a function of longitude, and two plots, one for 3 kilometres from the ice shelf front and one for 11 kilometres. The blue is the in phase, or we also call it apparent ice thickness measurement, and the orangey colour is the quadrature measurement. And then on top of that are the observations from drill holes. So snow plus ice thickness is shown in the orangey colours, and snow plus ice plus 0.4 times the sub-ice platelet layer is shown in blue. And I think the measurements are reasonable for unedited data. So what that's saying then, the fact that we multiply sub-ice platelet layer by 0.4 says that our conductivities are in this range. So they're lying between about 800 and 1500 millisiemens per metre. That's a solid, a nice volume fraction of 0.2 to 0.4, which is still a very large range. So if we turn this around and now say, well, let's plot up sea ice thickness and the thickness of the sub-ice platelet layer as a function of longitude. So this is a transect across the ice shelf front. The magenta is what we measure at 3 kilometres, the blue at 11, and the purpley colour at 16. I've put the ice shelf base at 0, and so the measurements upwards are consolidated ice plus snow, with measurements, plotted drill hole measurements on top, and underneath here the negative numbers are the sub-ice platelet layer thickness. So what can we see in sub-ice platelet layer as we move away from the ice shelf? First of all, we can see, not surprisingly, that the peak thickness is about 8 metres, sub-ice platelet layer beneath 2 metres of first-year sea ice, and that peak, not surprisingly, gets smaller as we go more distant from the ice shelf. It's also moving to the left because of Coriolis. So Coriolis is pulling the peak of that plume to the left. So that's under first-year sea ice. We've done flights when there's been multi-year sea ice in McMurdo Sound because of the iceberg B15. And so down at the base here, this is the McMurdo ice shelf, but all of this paler stuff, whiter stuff, is multi-year sea ice, and then the black area here is first-year ice. These are apparent ice thicknesses. I point out the blue here, which are very thick. So we're getting apparent ice thicknesses of up to 20 metres. So let's focus in on this little rectangle, which looks a wee bit more carefully at these transects. So here's a line A, which is largely on the first-year sea ice, and line B, which is closer to the ice shelf and largely over multi-year sea ice, although there is a gap here that got bitten out by an icebreaker coming in. So here's the transects through these. And our first reaction on seeing these data was that it was probably nonsense. Because if we look at the transect that's closest to the ice shelf, it would say that for about 20 kilometres, there's a sub-ice platelet layer that's in excess of 10 metres thick under multi-year ice. So again, this the base of the sea ice is here, sea ice plus snow, consolidated sea ice is measured upwards, sub-ice platelet layer measured downwards. So it's saying that on one of the transects that we didn't measure by hand, by drill hole, there's very thick sub-ice platelet layer there. And this is where we can look at satellite results. So what's plotted here are freeboard measurements against longitude, and the dark measurements are the IceSat freeboard measurements for the first year sea ice, and then the coloured measurements are IceSat freeboard measurements on different years for the multi-year ice. And if we scale these sub-ice platelet layer measurements and plot them on top, we find that actually the peak of the sub-ice platelet layer is a little to the right, a little to the east of the peak in the satellite measurements, but that can be explained because it was so very close to the ice shelf and there was Coriolis pulled it to the left. So this is some evidence. Without any other evidence, we can't say whether this peak on the multi-year ice is because of snow or because of something under the ice. But I would contend that perhaps this is some evidence that in fact it's the ice crystals coming from under the ice shelf that are affecting the observations here. So the most recent thing we want to do is move much further out into the Ross Sea. And so to do that, we need to not fly under a helicopter, but we need to fly under a DC-3. And this is Rosie under the DC-3 in McMurdo Sound. We were happy to get some results also from last year. Again, a line A and B that we've flown before so that we can compare the measurements from 2016 with the aircraft with the measurements from 2013 that were under helicopter. And the intriguing thing is that there are some features here, some details of this sub-ice platelet layer that appear to exist from year to year. Does this matter? I don't know. We recently looked at where sea ice appeared to be affected by ice shelf water outflows, and there was not an awful lot of evidence of these ice shelf water plumes affecting sea ice growth. We've coloured in blue, green, the places where we might expect some influence, noting again that minus 30 watts per centimetre, whoops, oh, I see what I'm doing wrong. Doesn't want to go backwards, sorry. Minus 30 watts per centimetre is a growth of about 1 millimetre per day. So where do we go from here? Scales. How can we compare drill hole measurements with airborne measurements, with satellite measurements? Do they even measure the same thing? The word validate I've put in there. I'm happy I put it in inverted commas because, you know, that's perhaps something we can't really do. It would be great to go to a survey of frazzle ice around the Ross Sea, because one of the reasons why there may be so few measurements is because maybe there just aren't any observations, because this of course is underneath sea ice. I wanted just to finish by acknowledging all the other people who are actually part of this study. Thank you.
We have time for some questions. have a sense of whether all these ice is being generated in the plume and then just deposited mechanically under the ice, or whether there's still sort of remnant supercooling in the water column below, into which those platelets can continue to grow on the bottom?
Yeah, the water continues to be supercooled quite a long way north. So it's not just being swept by currents. It's trying to think how far north are we measured. Certainly for tens of kilometres and beyond, you will measure supercooling near the in situ supercooling near the ocean surface. Yeah.
Other questions? My question then follows a little. Does that mean the platelet layer extends tens or hundreds of kilometres from the ice front?
We've seen platelet ice 80 kilometres from the ice shelf, and I don't know if it goes further. Yeah. And that's the point of having a helicopter or an aircraft.
Why do you think that the ice shelf is melting? Do you have temperature profiles or?
Oh, it's a well-known phenomenon, Alexei, that it's to do with the pressure dependence of the freezing point. So
No, why it is melting?
Yes, it melts because of the pressure dependence of the freezing point. If the water has come from the surface, there's a pressure dependence of the freezing point that causes it to melt ice at depth. I can explain it.
It also should depend from the temperature of an ice shelf.
Yes, of course. This is for cold water. This only is the case under a cold-based ice shelf that you would get this.
Do you know temperature of ice shelf?
At the ice-water interface, yes.
Yeah, that should be equilibrium temperature, but inside.
In time, do I know how it's
inside.
changed?
Inside ice shelf.
No, Paul, do you know?
No, it does, maybe.
But I mean, there aren't many measurements. The last measurements were sorry, Paul, what were you going to say?
I was going to say, you do know the temperature inside the ice shelf, but the conduction of heat into the ice is only about 10%. The dominant balance is the sensible heat flux from the ocean, with the latent heat release of the ocean.
And how cold is inside?
Minus 20, minus 30?
And what is the distance from the interface?
A few hundred meters.
Few hundred.
Yeah, so it's that's what makes it very different. So this system is for sea ice, very different for marine ice, because there isn't the heat flux upwards.
Any other questions?
If not, let's thank both of our speakers.